We stopped here in the previous video, and now we proceed with this. We're going to assume these guys are constant, and instead of carrying these all over the place, we're going to replace all of that with D, just for brevity in the nomenclature, right? So how did we get this? We basically took this out of the brackets, right? And we have delta x squared here, right? Multiply both sides by delta x squared. So you have delta x squared over delta t. And this becomes just that. And that's where this showed up. The other terms are identical with this. So now you can write that equation in this form. This is all d. So d times these two, right? That's all you have. So you can separate it out. dp2. Here, P2 is at what time step? It's at time step T. All these P's are at time step T. That's the current time step. And this P2 is at the previous time step, and it came from this first order backward difference. So we've just expanded this out, right? So dp2 minus dp2 at previous time step. And all of this is at point P2. And we can rewrite that. We can use this same relationship to figure out the equations at point 3, 4, 5, at all the other points in the domain. Now you see you can actually rearrange these, right? The P2, there are terms, there are common terms here. P2 is here, P2 is here. So take this to the left-hand side and it becomes what? P1 minus, this is going to come with a minus, right? So minus 2 plus D, right? P2. Other terms remain the same. This is P2 at T minus delta T, previous time step. And that's what you see on the next slide. That's precisely this, right? Exactly what I just wrote down on the previous slide. And now, just by analogy, you can figure out the values at P3, P4, P5. So for P3, this is for P2, right? So 1 becomes 2, 2 becomes 3, 3 becomes 4, 2 becomes 3. Same here, 2 becomes 3, 3 becomes 4. Just increment everything by 1. That's how to move from one pressure point to the next, and on and on. Move 1 point. How about P6? Do we just move 1 point? If we move P6 1 point, you're going to end up having P7, but there are only 6 pressures in the domain because P6 was the last one. So this is P6. 5, 4, 3, 2, and P1 here. So there's no P7, so we can't just continue incrementing 1. We need to treat the boundary condition differently. And what did we say about the boundary condition on the right side? We said we're going to use constant pressure boundary. We're going to fix that at PWF. So this is what is known as a Dirichlet boundary condition. So P6 is just going to be set to PWF, which is a constant value. How about P1? We're going to use a no-flow boundary, right? So technically, we are saying Q equals 0. So you will see that the way we're going to implement it in this formulation is we're going to artificially create another cell here, which will be a mirror image of this pressure point. So this will be P2 again. Why? Because if this is a mirror image of that, the flow that should be going away from this will be balanced by flow that should be going in this direction. So this will be a no-flow boundary condition. And that's the idea that is used in this setup. So artificially create one point here, which is a mirror image of this. So the flow in this direction will be balanced by the flow in this direction, and this pressure will be P2, just like this. And automatically P1 will be a no-flow boundary. So that's the concept known as the use of image, the pressure image, to create a no-flow boundary. And so if you were to write the previous equation in the form of the other ones, right? I mean, the equations we're stepping through for P2, for P3, for P4, for P5. The middle term is this. It will be P1, right? Plus P2. This would have been P0, which does not exist, all right? But what is P0 going to be in this case? Using the image convention, it's going to be P2, so that it's symmetrical with that. So that's what you see here. That's why P2 shows up here and here. And now you can add those two pressures together, and it's 2P2. So this is the equation for P1. And if we write out all the equations we just derived in this form, there's the equation at P1, P2, all the way to P6. And these are the corresponding right-hand sides. And you note that these pressures are from the previous time steps. And you will later see that anytime you can write out multiple equations in this form, you can actually represent it in a matrix form. So this is a linear system of equation. This linear system of equations, why is it linear? Because we have assumed all the parameters in D were constant. If those parameters, meaning phi, rho, mu, ct, are functions of pressure, then, or even k, then the equation becomes nonlinear. If just one of them is a function of pressure, any parameter in D is a function of pressure, the equation becomes nonlinear, because pressure, which you see we're solving for, now shows up as part of the coefficients. Anyways, this is the system of equations for all the 6 points. And now, before going ahead to solve it, we want to estimate the D, right, which we had written in this form. So we need these parameters. So we assume these parameters. Total length of the domain is 1000. We already talked about delta X being 200 feet. This is the initial pressure, flowing bottom hole pressure, total compressibility. And these are the viscosities, permeability, and porosity respectively. So just plug in those values here, and this is what you get. Of course, delta T has to be in hours in the form we had written out this equation. So this is what you get for D. So in place of D in the equations, in the system of equations, use 0.158. Initial pressure everywhere was 2000 psi, and that's going to be used on the right hand side of the equation, as you will see on the next slide. So P for cell 1 at the previous time step, which is the initial time step, we're trying to evaluate. So we start out at 0. Every pressure everywhere is 2000 psi. Then you start moving in time, so that's time 0. Then you start moving forward in time and then evaluating the pressure. So P1, P2, P3, P4, all the way to P5 at the initial condition is 2000 psi. How about P6? Remember, we said P6 everywhere is PWF, which is 1000 psi. That's flowing bottom hole pressure. That's why you don't see us write P6 here. So you will never really solve for P6. You're just going to fix it at 1000 psi. Okay. You remember the right hand side was D multiplied by the different pressures, right, at the previous time step. So we already figured out D from the previous slide, which was this without the minus, right? Now multiply that by the initial pressure at the previous time step, which is the initial time step. It's 316. So D will never change. And you're going to see this term show up in the linear system of equations. So that's what it is right here. We are trying to solve it at time step. So this is at time delta t. The previous time before delta t was 0. So when you move forward one time step, all these guys are 316 as calculated here because they are all minus d1, except P6, which I mentioned. It's 1000 psi. You see that here. And these are the D's, right? This MD, which is 0.15802. And then the next slide I'll show, in the next video, I'll show how we're going to be able to set up this system in matrix form.